In this video, we'll talk about ideal gas processes. Ideal gas processes can often be represented in a PV diagram, where in the diagram, the x-axis is the volume of the gas and the y-axis is the absolute pressure, where the absolute pressure is the sum of the gauge pressure and the atmospheric pressure. But what's the benefit of using a PV diagram? The answer is energy states can be instantaneously represented in such a diagram. The dot product of the pressure and the volume, where pressure has dimensions force over distance squared and volume has dimensions distance cubed, that dot product ends up being the dot product of force times distance, which is work, which is a type of energy. If a container of a volume of gas is pressurized, the molecular impacts of all the molecules inside rebounding against the outer surface wall is what creates the pressure. To illustrate that, I'm showing a volume of gas inside a container. The volume gas contains atoms or molecules which have velocity and impact and rebound off the outer surface of the container, and therefore this creates forces, and the sum of those forces is what we call pressure, which acts over an area. So there, if we look at the pressure vector, which is normal to the outer surface area, it ends up being in parallel to the dA vector of that surface. For these videos, we'll only be talking about closed systems. Closed systems are systems in which there is no flow of this gas into or out of what we define the system. So therefore, there's be a constant number of moles or molecules of this defined gas comprising a single homogeneous volume within that system. If during the process the volume increases as shown, then the internal closed system inside that volume will do a positive work on the surrounding outside that closed internal system at the boundary interface between the system and its surroundings. The ideal gas law is given as PV equals nRT, which is energy equals energy. As we just learned, pressure times volume is energy, and then therefore nRT is also an energy term, where N is the number of moles, R is the universal gas constant, and T is the absolute temperature. So we're dealing with absolute pressures and absolute temperatures. So therefore, both the right and left side of this equation can be thought of as energy because that's what they are. The right side is the internal thermal energy due to the internal kinetic energy of all the molecules or atoms of gas inside the closed system. We're working with ideal gases, and ideal gases have assumptions including one assumption is all energy states represented in the PV diagram are states of equilibrium, where all the variables that describe the state, such as pressure and temperature, are equal throughout the entire system and have reached equilibrium and not changing with that state. There's another assumption that the system is an inertial frame of reference, therefore the entire system is not accelerating. The closed volume is not in a centrifuge, or the closed volume is not inside an accelerating container. Another assumption is there's a very large number of molecules, each with the same mass, for example, the same isotope of gas inside the closed system. Another assumption is the average distance between molecule or atom is much greater than the diameter of the molecule. The molecules are assumed to obey only classical Newtonian mechanical laws, and that all impacts with other gas molecules or atoms or all the surfaces are totally elastic, perfectly elastic, and last a very short time with only kinetic energy changes and no potential energy impact effects. Another way to say that is the volume of the molecule is very small compared to the total volume of the system. This, however, does not mean we are considering the molecules to be particles in the classical Newtonian sense, in that the molecules have no rotational kinetic energy, as we'll discuss later. The ideal gas law also assumes that there are no intermolecular potential energy forces of attraction or repulsion between the gas atoms or molecules. Two common gases for which the ideal gas law is often applied are monatomic gases and diatomic gases. Where monatomic gases are typically the noble gases such as helium, neon, argon, etc. And diatomic gases include hydrogen, nitrogen, oxygen, chlorine. The monatomic gases have their lowest energy state where the single atom is represented, and the diatomic gases have their low energy state where two atoms combine. In the graph shown, U, the internal thermal energy to the internal kinetic energy of the molecules or atoms of gas, with units joules per mole in the SI system, can be shown as a function of the absolute temperature K. The slope of the internal thermal energy due to internal kinetic energy of the molecules or atoms as a function of the absolute temperature, defined as the molar specific heat at a constant volume, which is equal to the number of degrees of freedom that kinetic energy can exist in that gas, divided by 2 times the universal gas constant. The equipartition energy theorem derived by Boltzmann and Maxwell state that every degree of freedom that appears in each quadratic energy term contributes equally to the total internal energy. Stable monatomic gases have 3 translational degrees of freedom that each provide the same amount of kinetic energy. There can be kinetic energy of translation due to velocity in the x direction, the y direction, or the z direction. These monatomic gas atoms have no rotational degrees of freedom and therefore have no rotational kinetic energy terms. Since these monatomic gases have 3 degrees of freedom, the specific heat at constant volume of these monatomic gases is 3 over 2 times the universal gas constant. In contrast, diatomic gases such as nitrogen, a molecule of nitrogen has 2 nitrogen atoms. Therefore, that molecule has, once again, 3 translational degrees of freedom due to velocity in the x, y, and z direction. However, since the molecule is not a particle, it does have rotational kinetic energy. This rotational degree of freedom and this rotational kinetic energy, in contrast to translational, there's only 2 degrees of freedom. Since the shape of the molecule is such that in the third rotational degree of freedom, rotation in that third degree of freedom results in the molecules, as the shape of the molecule is indistinguishable in the third rotational degree of freedom. Therefore, for diatomic gases, the slope of U, the internal thermal energy due to internal kinetic energy of the molecules, relative to temperature, the absolute temperature, has 5 degrees of freedom divided by 2 times R. Therefore, using the ideal gas assumption, at any absolute temperature state, a diatomic gas will have more internal thermal energy than a monatomic gas. Also, the assumption with the ideal gas law is the internal thermal energy at an absolute temperature of any monoatomic gas, such as helium, neon, argon, will all have the same internal energy. The internal energy of these monatomic gases do not depend on the molecular weight. Similarly for diatomic gases, although hydrogen and oxygen and chlorine have significantly different molecular weights, at the same absolute temperature, they will have the same internal and thermal energy. Unlike these ideal monatomic and diatomic gases, the internal thermal energy of compounds such as carbon dioxide or methane tends to increase with the molecular weight at a absolute temperature state. A further discussion on this topic is beyond the scope of this video. Since both monatomic and diatomic ideal gases have their 3 translational degrees of freedom, velocity in the x, y, and z direction Cartesianly, the root mean square of the gas velocity for both cases is the same, where the root mean square is equal to the square root of 3 times the universal gas constant times the absolute temperature divided by the molecular mass. Therefore, for example, hydrogen with a low molecular weight will have a much higher root mean squared velocity than, for example, chlorine. One can also see with that equation that the root mean squared velocity is proportional to the square root of the absolute temperature. Higher absolute temperatures, higher root mean square velocity, higher thermal kinetic energy. And since kinetic energy is 1/2 mass times velocity squared, translational kinetic energy is proportional to temperature. As can be seen in the graph, when the absolute temperature is 0, this corresponds to 0 internal thermal kinetic energy. Recalling now that for my ideal gas law, product of pressure times volume is energy, and that equals energy, which is nRT. Both sides are energy. In the PV diagram, I think is very helpful to show lines of constant internal thermal energy, which, since internal thermal energy is nRT, it's proportional to temperature. These lines can be they're often called isothermal lines, but they're actually both. They're isothermal lines, and they're lines connecting states of constant internal energy due to the internal kinetic energy of the atoms or molecules. For example, looking at one of these blue lines, that blue line represents the exact same temperature at all these states. And since the temperature is the same, the product of temperature times the constant, universal gas constant, times the constant number of moles in that closed system all represent the same amount of internal energy. So therefore the product of pressure and volume is also the same. So I can have on that singular line a large volume and a small times a small pressure, or if the volume is decreased, then the pressure goes up and it follows along one of those singular blue lines. As you go closer to the origin, then the product of pressure times volume is lower, which represents a lower energy state, and therefore it's cooler. So therefore the lines that radiate farther outward and outward represent higher internal thermal energy or a higher temperature. Therefore, I recommend whenever you use the PV diagram to represent ideal gas processes that you immediately draw some internal thermal energy lines or isothermal lines on your graph, and remember that the farther out from the origin they are, it's the system is at a higher temperature and it's also higher internal kinetic energy.